Hi everyone, my name is Camila, and this is Joaquim. We are from PSR, and we want to talk a little bit about our experience with Julia. So, for those who don't know, PSR is a provider of analytical solutions and consulting services since '87 in Brazil. Our team consists of around 60 people, the majority of which holds at least a master's degree. So basically, we have three different groups of people: the consulting area, the providers of analytical tools, just like me and Joaquim, and the IT who provides the support to us. Some of our core activities, so we develop analytical tools, we provide strategic advice, market regulatory design, environmental analysis, engineering studies in general, some of which we're going to talk a little bit about today. So some of our recent projects, PSR have projects all over the world, all over 70 countries and through all continents. We have over 300 active licenses worldwide from our softwares. I'm a researcher and developer since 2013. I have a master's in electrical engineering, and I'm basically in PSR and outside as well. I've been programming several different languages. Julia is the most recent one. I also wanted to say that we from PSR invest a lot on research. This is some of the research that we've been doing lately. So we have been using SDDIP. We have been providing research for reliability analysis, expansion planning of reactive power flow. This is my work, immediate cost function, which is an algorithm to speed up SDDP problem solving. And just for you to have a sense, in the International Conference of Stochastic Programming of last year, we sent about 15 people. So we really care about research. And those are the main tools we're going to talk a little bit about today. So SDDP is our stochastic production scheduling optimization tool. OptiGen is our capacity expansion planning optimization tool. And OptiFlow is our optimal power flow for reactive expansion. So our experience with Julia began with, we use it to test new ideas, basically. So we did it for several different types of model. We did portfolio optimization, which motivated the creation of the API of Express in Julia, which Joaquim was the responsible for. We did power systems reliability analysis, in which we use Monte Carlo methods, network flows, Fourier analysis, so very complicated models. Decomposition of integer programs. We've been dealing with Julia for quite some time now. This is the first SDDP code that we did. Joaquim was the responsible for that. Nowadays, it's very different from that, I promise. So after a while, we decided that we were very pleased with the performance of Julia, so we started using that in production. So we already use Julia for actual real-life projects. So we use it for the Peruvian system, the Chilean system. We actually also use it for portfolio optimization for the NGO called the Nature Conservancy. Basically, what we did was to choose the best set of hydro plants to build in the Magdalena Basin River, one of the main rivers of Colombia. It's a very interesting study. You're gonna find a reference of it in our website, which I'm gonna give you later. We also use this to evaluate the interconnections between Latin American countries for the Inter-American Development Bank, and refactoring Genesis from NWPCC.
Okay, now it's my time. It's a pleasure to be here. So my name is Joaquim again, and I'm graduated in telecommunications and mathematics. I'm currently a PhD student in Rio. I'm also a researcher and developer at PSR since 2015. And as most of you, maybe all of you, a Julia developer. My history started when I came back from the US to Brazil in 2015. And I was like a C programmer that had many, many hours with MATLAB and R. And in my first day, my boss was like, "Have you ever heard of Julia?" And I said, "No, never." And so here it is. And Jump was already online, and our company is really into optimization. And so I started using from that day on, and Julia's started giving really, really, really good results and a lot of flexibility. Thanks to Jump that was already alive at that time. This is a first picture. We've been talking about SDDP, so what is that? After all, it's actually an algorithm, but it's used for power system operation, at least for PSR, most of the time. This slide just shows how complex can a power system be. So I just threw in a lot of words, and just to show that there's a lot of details to take account, and even much more than these. So there are a lot of details from hydro plants, a lot of details from thermal plants, renewables, transmission networks, all that coming to play together make a really, really hard problem to solve. Moreover, the problem is stochastic, because in many countries you have the big presence of hydro plants, so inflows that are stochastic make the problem even harder. In other countries, you have uncertainty on fuel costs or wholesale energy market prices. So all of that makes the problem even harder. So let's go a little bit deeper with algorithms, since everybody here just did a little bit of when technical. Let's do it also. So why do we need a different algorithm other than just writing a big optimization program and solving it at once? This problem of hydrothermal power systems is coupled in time, because with hydro plants you can transfer water from one month to the other, and that is a reservoir of energy. So you have this big time coupling, and it's important to solve multiple stages together. Also, the problem is stochastic due to the parameters I talked about in last slide. And so writing all that in a linear programming, whatever that is, it's really, really hard. And sometimes it's not even feasible. It's not doable on a regular sized computer, because you have too many scenarios, stages, and you have something called a scenario tree that grows too fast if you want to represent uncertainty in a reasonable way. So SDDP stands for Stochastic Dual Dynamic Programming. We talked a little bit about dynamic programming in the first keynote today. This is an algorithm developed by Mario Pereira. It's PSR founder and president, but it's kind of widespread. In this international conference of stochastic programming that Camila mentioned, we have 5 dedicated sessions on that and more than 22 talks. And in Julia, it's surprisingly incredible how many SDDP are being developed right now. There is at least 3 libraries that I'm aware of. One of them, the writer is over here. And many more others that are being developed. So Julia seems to be a very good environment for doing multi-stage stochastic optimization. Something about our current implementation of SDDP before Julia. It's a Fortran code with hundreds of thousands of lines, but it's really, really hard to maintain that, and writing optimization models in non-algebraic notation makes everything harder. So we are looking forward to something that makes it easier to maintain and to add new features all of the time. But the current framework is hard to beat in not too much time, because we handle really big power systems. For example, in the Brazilian power system, we have to solve more than 1 million optimization problems, which is kind of hard, and we do that in Amazon clusters. Okay, because the algorithm is really good for distributed processing. So STDP has been running on computer networks since 2001, and from 2016 we are using Amazon. We are the first case in Latin America of using Amazon for large-scale computing. I wouldn't say large-scale, since the Celeste project is slightly bigger than this. Okay, more on STDP. So in this decomposition algorithm, we split. I said we had stochastics and time coupling. So we split all the problems of each stage in smaller problems. So you have one stage for one realization of a stochastic uncertainty, and that's what we call a subproblem. And the algorithm works in two main steps. The first one is a forward simulation in which the states are propagated in time. So volumes of your reservoir are propagated in time. So you have a policy, you have a simulation of your power system. And there's a second step, which is called a backward recursion. In this second step, we approximate something that we call a future cost function, but other people know as cost to go function, or even a Bellman recursion. So we make a lower approximation of that, and this iterative lower approximation is what makes STDP interesting. And after all, since it's stochastic, we have a stochastic convergence check. Let's try to explain a little bit of this with some images. Some people were successful today. Let's see if I can get at least a little bit for you. So this is a subproblem of in a mathematical programming form. It's not really important the form of it, but it's important that you have an objective function that is composed by a term that does not depend on the future, and a term that depends on the future, which is the Bellman recursion term. You have a state space equation, which is this water balance equation, which means that water that you do not use in this month, you keep to the next month. You have load balance because you're solving something for power systems, and you have stochasticity that comes into play in this autoregressive model. The actual model is much more complex than this, but this is a reasonable archetype so that all of you can get a glance on what it means. So let's go for the algorithm. Here I'm representing we will solve a problem with 3 sequent months, and all these months have these cost functions of their own, but the problem is that we do not know the cost functions of each month. So we are going to approximate them iteratively in the 2 processes that I just explained, after a forward and a backward pass. So in the x-axis, we can see some state variable, maybe the volume of some reservoir, and the y-axis is the cost of operating the system at that time. Okay, so we start by obtaining a first state of the first month, and then we proceed in a forward manner. We solve the following optimization program, and we go to the second state of the second problem, and we obtain now the third state of the third problem, and this is what consists of a forward iteration, which is a simulation of what might happen in your power system. But now you go backward, estimating these cost functions of each stage. So we make a lower approximation with a hyperplane, and then we iterate backwardly and create an approximation of the hyperplane for the state before that, and then you do that again. And once you have that approximation, you can go forward again and estimate a new path of reservoir volumes. And after the second path, you go backward once again. And then you improve your approximation at each stage. And that's what the algorithm consists of. And then you keep going forward and backward until you have a fair representation of these cost functions, at least where your volumes are staying. So this is the basics of the algorithm. Hopefully everybody gets that. Just a little bit more, these are some applications of stochastic dual dynamic programming in power systems. We have been using that for valuation of studies in new projects, assessment of regional markets and international connections, system price forecasting, mid and long-term production planning, regulatory studies and market design simulations, water resource analysis, natural gas versus electricity coordination. A little bit about what I had in my implementation of STDP. So it was really important that we were using something that is easy to prototype and test new features. As Camila explained, we presented many papers on the last conference on stochastic programming, and many of them were based on this implementation, which was really easy to build new concepts over this. And it was very good that we had good performance in this easy to prototype language. I'd like to quote some phrases from Miles Lubin, one of the creators of JUMP. He said that he wanted to model and solve LP and MIP within a programming language, but not Python because it's too slow, and not C++ because it's too low level. The problem is that you have algebraic modeling languages like AMPO and GAMS, but they are not within a real programming language. And so dealing with other data structures in your program, it's much harder, and you have to combine those with Fortran, C, or even Python. But maybe you could put everything to the same thing. And so I think that's what Miles thought, and Julia was the perfect place for that. And then there was an STDP on that, and for example, I was testing that on my computer last night, and I had an example for Central America in which each sub-problem, that means a problem for one stage and one scenario, has 2,500 variables and 25,000 constraints. We had 60 stages, 100 scenarios, and 5 iterations of the algorithm, because that converged right after that. For that, we had to build an optimization program and send it to a solver at least 200 times, and we had to solve the problem 1 million times. And all of that can be done in 20 minutes in this notebook. Of course, as the system grows up, like Brazilian system, you cannot do that. If you consider more constraints, it gets even harder, and it's impossible to do in this computer. And that's why you go to bigger clusters. We got very good results using Julia, because more than 70% of the time of the algorithm is spent inside the LP solver, Express in our case, and that thanks to this, I saw that thanks to this nice package, timer outputs. Something also that was really, really useful is that MPI was really easy to plug, because the wrapper was already prepared in Julia, and so I could change my model from running in series to a model in parallel in a matter of a week or two, maybe. A little bit more about implementation. Something else that Miles says turned out to be very important for me. He wanted to make it easy to access low-level features of solvers. So JUMP and MathProgBase, which is what is behind JUMP, would not get in the user's way. The problem is that JUMP is really, really nice for creating problems, but some specificities of linear programming are problematic to use in higher level stuff. For instance, we have in STDP this thing that is called a cut relaxation or cut selection algorithm, in which you write the basic problem and you iteratively or add just a bunch of constraints, not all of them. You just choose a few of them to add. And doing that in JUMP turns out to be a little bit slower for our purposes. But that's okay. MathProgBase was over there and was already low level, so I could use that part, you could write that part of the algorithm in a low-level language. Moreover, other details of the implementation. This thing of building problems is really hard, and so you have to keep not building many of them, just build a few of them, and then just modify them. So, for instance, if you already built the problem for month 1, and you want to solve that same problem, but for the second scenario, you just change a few parameters. Because building a problem is sometimes much more expensive than solving this problem. So we managed to use lower level features of the solver API, for example, removing variables, removing constraints, changing coefficients, fixing values, and all that was only possible because accessing that was very, very easy. Also, varying parameters in the solvers was very important at that point, and more stuff that came into place later was doing many operations in place, and you can do all that, but it wasn't possible to that stage to do that in Jump and Matprog base. But we've been to the Jump developers workshop last week, and after that we redesigned a bunch of features of Matprog base, and that's going to scale to Jump. And hopefully many of these features that I said that I had to go low level to reach them will be available in the standard Jump API.
So I'm going to talk a little bit about our expansion planning model. It's been used for several years, and it's able to plan expansion in systems throughout several decades. So it's a really powerful tool. Basically how it works is that the user chooses candidate projects, so hydro plants, thermal plants, renewables, gas pipelines, interconnections, and then after the model decides the expansion plan, then the problem goes to SCDP, and we obtain an alternative estimation of the operative costs of that plan. And there's a lot of available input data. So let's say, for instance, you have 2 hydro plants that are in the same or similar heights in the same river, so you have to tell the model that they are exclusive projects, so you cannot build both of them. We have association constraints, we have budgetary constraints. It's a very complete model. And as I mentioned before, it is a 2-stage model. We use a Bender's decomposition. So in the first stage, our model chooses investment plan, and then it goes to SCDP. We obtain operative costs until we reach the convergence and we find the final optimal expansion plan. Several applications of Optigen throughout the world. So there's a lot here, but I'm just going to mention that it's used by the World Bank. It's used by market operators, regulators, investors. There are several very recent studies of expansion planning, transmission, and generation in South and Central America. So what's the big challenge we have with Optigen? So the model is built in Fortran, and it's a steep learning curve. So we have 36,000 lines. It's much smaller than an SDDP, for instance. Our SDDP solution in Fortran has 124,000 lines. So this is much smaller, but even though it's not very intuitive. So for new programmers, it gets hard. So the code is rigid. It's made to do exactly what it makes. So if you want to test something new, we have to go through the whole model and change every single thing without even knowing if the idea is good or not. So I've put some examples of Fortran. I'm not gonna mention about it, but you guys, pretty much everyone here, I think, had an experience with that. So you all know it's tough. And a little bit of context about what's happening with the energy market, which is quite a trendy topic right now, renewable generation. And this is why we've been adapting our models nowadays. So we have an expansion, considerable expansion in renewable energy. I have some data in Central and South America, but also China has been going through a huge expansion in renewable sources. Germany has some bold goals in renewable expansion. And this type of energy sources, like all others, has consequences. So I brought here, this is basically the total wind generation of our northeast system in Brazil. So the red line and the blue line are 2 consecutive days of the total generation of the system that has most wind power plants in Brazil. So you can see that throughout the same day, there's a lot of difference between the generation from hour to hour. And also if you compare same hours in consecutive days, you can see that the difference is quite considerable, especially if you think about our Northeast system, which has around 5 to 6 gigawatts of capacity of wind generation. So a variation of 1 giga is a lot. So what we did is, instead of rebuilding the model, we made a completely new formulation in Julia, focus on energy reserve, focus on the fact that renewable projects can have uncertainty generation outcomes. So it's an integral model. And we're able to balance the economic benefits of having renewable sources projects, but also what are the consequences to the operation of the system when we do decide to build them. So this approach is completely adapted to renewable generation and battery projects. We were able to test different decomposition approaches within days. It was super simple to test. And it's a much smaller model. It's like around a 4,000 line model. So it's much, much simpler for a new person to understand and be able to help us. It also motivated some more work in the API of Express. So for instance, we needed the optimal solutions, the current best optimal solutions iteratively. So if we decided that we wanted to stop before we reached our tolerance, we wouldn't lose the best solution we could get. So we had to make some small changes, but it was easy. So this is a tool that's already been used in several real studies. We've been using it for obtaining the expansion of Saudi Arabia, Colombia, Chile. We've been using it, as I mentioned before, for the Inter-American Development Bank. But I brought to you the expansion planning of Saudi Arabia just for you to have a sense of what we do. So Saudi Arabia is a very interesting case because it's a 100% thermal system. And 15 years from now, its energy demand will basically double. So we're talking about a huge expansion plan. And so basically the results here is that instead of only investing in renewable plants, we have, because of the reserve constraints and because of the fact that they are uncertain, we have to invest also in thermal plants. And you can see that the fact that we added reserve requirements to the system also made our model to invest in 10 gigawatts more of additional installed capacity. So this is the effect that reserves have in our optimization model.
Okay, almost at the end of the talk. This is the last model, the last two we were going to present today. So OptFlow is originally focused on nonlinear optimal power flow for reactive expansion. The original model is a tailor-made interior point method. It's extremely fast, however, it's very, very hard to add new constraints and prototype new ideas within this framework. But the new version, everything is based on jump. and is designed to accommodate nonlinear power flow and many of its convex relaxations. So it's very useful because it's ready to generate valid cuts for the composition algorithms, just like SDDP. And it's very easy to test new ideas. For instance, progressive hedging is a stochastic programming technique that it's not very hard to program, but we could do that in less than a week, and it was awesome because we were in Julia. That was so fast to happen. Upflow is also similar to this library that is online by the guys of Los Alamos. It's called powermodels.jl. You should take a look of that. It's very interesting because we do just like they do. We abstract on constraint classes because PowerFlow has these nonlinear constraints which can be represented in different forms. For instance, nonlinear rectangular, nonlinear polar form, convex second-order cone programming form, convex semi-definite form, either complex or real form. And you can write all that in Julia, compare all the results really fast, and choose your favorite model, the one that gives you best results in less time. And that was very useful. Here are some testing comparisons against our model in Fortran. The problem is that the Fortran model is very, very specialized, and it's already prepared to change some coefficients in place, so it does not have to build the model every time. But we are very happy with the current results that we were solving 12,000 problems, and we had this slowdown of a factor of 10 from our Fortran implementation, but we're using a generic solver. We have not optimized everything yet, so we're quite confident that we can get even closer. Even though the solver time is much larger, we can just change values in place and use warm starts to improve those results. So really looking forward to improve that. I think Julia has much to offer in this sense. Now a little bit of our difficulties of moving to Julia. Maybe many people here had similar problems. Maybe you had different problems. Everybody at PSR is fluent in Fortran, so if you want to help in Fortran, you can just ask for somebody that sits by your side. Hello, can you give me some help with this code? And that's it. And there's a lot of examples ready. Julia, we have an awesome community, but sometimes we don't have nobody never tested anything similar to what you're doing. But we keep asking questions on the forums, and everybody keeps helping. Moreover, Julia has this problem that so far we have this big environment because we include many libraries inside that. So sometimes creating small executables is a big problem for somebody that has a client, and this client just asks you, oh, can you give me a software that does that? And you just want to give him a small executable that does some simple work. And that's sometimes a big problem. Part of that will be solved for what Stephen Karpinski mentioned it in his package 3 presentation yesterday, because reproducibility of the results so far, it's a small problem because you have a piece of Julia code that depends on other libraries, and you send that to somebody download the libraries, but they are in a different version than yours, and so the person kind of has different results if they can't run the code at all. Sometimes that's a big pain. Also, Fortran and many other languages that are over there, they have more time living, and so they're easier to debug, and in some interfaces, just like Visual Studio. In Julia, we used to have debug.jl. That was very nice in Julia.4, but as soon as we moved to Julia.5, we expected to use Gallium, but it was ready, but not that ready, and so it was really, really hard. So we're looking forward for the new version of Gallium or something like that.
No pressure.
But also many benefits besides many of those that I explained during the talk. it's very good to be in a high level and very efficient language with very good optimization environment thanks to the JuliaOpt community. And something else that's very useful is that the C interface in Julia is so easy that we can use many of our own legacy code and generate automatic interfaces, and then every piece of that is readily available for ourselves, and we can use that in Julia very, very easy. And it's very good that we are in an environment for parallel computing, since many of our algorithms and methods are very easy to parallelize, and it's a very good thing. So that's all for today. Thank you, and if you have any questions, we're here for you.